Hello everybody, I'm Maurizi from the Norwegian University of Science and Technology. Today I'm going to show you a brief presentation on energy-based approach for refining assessment of 3D architectural materials. This work has been made in collaboration with Bryce Edwards and Julia Greer from the Caltech University in California. So let's talk about before 3D architecture materials, what they are and why they are important. Many researchers in the past have found out how some biological systems have a peculiar structures at the micro or nanoscale. In fact, they exhibit a specific mechanical properties, structural properties, and they are able to overcome sometimes the trade-off between the lightness, strength, and toughness. Replicating these architectures by means, for example, 3D printing, additive manufacturing, here you can see, we can recreate some architecture materials from a range of millimeters to nanometers. Of course, there are a lot of classifications for 3D architecture materials. The first classification which has appeared in literature was that of made by Ashby and Atkinson about random or periodic forms. And here you can see only periodic architecture materials because they are stronger fixing the relative density, which is this letter the content of volume material inside a specific geometrical volume. Here you can see classification of such materials like a truss-like lattices that are the lattices we have used in the present work, or plate and shell based lattices, everyone depending on the smallest element we can repeat to tessellate the space in a periodic fashion. The Greer group in the last 10 years found out how additionally at the smaller scale, at the micro and nano scale, a particular size effect occurs. This effect can be summarized, for example, for some materials as smaller is stronger or smaller is more ductile. And joining these two properties, the architecture and the feature size, we can design and tailoring some properties by exploiting of these two properties and creating 3D architecture materials. What we are interested on is mechanical and fracture properties. Specifically, these latter are the main point of the present work. However, in the literature, we can find a lot of works on mechanical properties. For example, here you can see the Young's modulus as a function of the density of an architecture material, and a classification depending on the rigidity of the unit cell as a stretching dominated or a bending dominated one. And in the present work, what we have used is a topology, a rigid topology for truss-like lattice, which is an octet truss. First of all, the Greer group performed the fracture toughness measurements, and here you can see the setup on the left, which is a scanning electron microscope with an indenter tip modified to perform experimental measurements tensile tests, as you can see here in this picture, on CT specimens, for example, fabricated by means of additive manufacturing, and in particular with the two-photon lithography method. And more in detail, they applied the mode 1 on this specimen. They've used a base material, a photoresist polymer, an octet topology, a relative density of 70%, a unit cell size of 7.5 micrometers, which is the length of the cube, which includes the unit cell. So we have performed, first of all, finite element modeling of the single unit cell to understand how the stiffness varies with the relative density and to see the difference between a beam Timoshenko element model and a solid element model. as you can see here in the picture on the left. We found out how the gap between the two models in terms of stiffness increases as the relative density goes higher, up to 70% of gap at 26% of relative density. Another interesting fact is that the stress concentration factor at the lattice nodes is responsible for the failure at the lattice nodes. In fact, experimental evidence shows us that failure is always at the nodes. Therefore, we have built a 3x1x2 octet tessellation with a notch and the relative density of 26% under mode 1. And we obtained a stress concentration factor between 2.5 and 3, computed as the ratio between the maximum stress at the intersection of the beams and the stress at enough distance to that point. However, we have noticed how building a solid element model to replicate the fracture experiments is prohibitive in terms of computational cost. Therefore, without generality restrictions for the energy-based approach, we try to validate such energy-based method on a beam element-based model. Therefore, in the left here you can see the bulk material, and on the right the architecture one. The hypothesis is that to have notch or a curve length much greater than the cell size, and we have to know that the length scales of the formations are at two levels, at the unit cell size and at the specimen size, and these levels can be seen here in the picture because the deformation map matches the deformation on the bulk material. So the first point, or the main point of this work, is to readapt the average strain energy density failure criterion to architectural materials. Therefore, the criterion is based on the fact that the failure of the material occurs when the average strain energy density on a control volume around the notch tip reaches a critical value. So here you can see the strain energy density formula, which is the ratio between the total strain energy on the elements inside of a specific geometrical volume divided by or the material volume or the geometrical volume. And by these two definitions, we can obtain two values of the strain energy density averaged on the volume, which are related to the relative density. Analyzing what happens to the material and the geometrical strain energy density averaged on a specific volume around the notch, we obtain these two behaviors. On the left here, we see that the strain energy density average on the volume around the notch is not so influenced by the relative density. However, for the geometrical value, we have a great influence of the relative density. And this is true also for other unit cell sizes. Indeed, we can see here for two values of the unit cell size of 5 micrometers, 7.5 micrometers, as a distribution as a function of the control volume size of the strain energy density is pretty the same. And if we normalize, we can see here on the inset the values of the strain energy density to the half of the unit cell size, we obtain a kind of invariant with the unit cell size. And this might be important for future observations. So first of all, we have to decide the control volume for the criterion. To do this, we have taken inspiration from a work of Pasquale Gallo and Kitamura on fractures of materials, and here you can see the strategy density distribution of the finite element model around the notch for different unit cell sizes and different relative densities. We see here that for every combination of random values at every relative density unit cell size, the concentration of the strategy density is prevalently on the first unit cell. And this can be confirmed by looking at the derivative of the strategy density as a function of the control volume steps. And you can see that the highest change in the derivative corresponds to one cell size of the control volume. Therefore, we have assumed that the critical strategy density at which the material fails is equal to the critical energy of the constitutive material. And besides, we have assumed that the geometrical A set value is the value which determines the failure of the material, since the material value does not depend so much on the relative density and in turns on the stiffness of the material. Therefore, here you can see the displacement at failure as a function of the relative density as well as the load at failure for two different unit cell sizes. And by considering the load at the first beam fracture occurrence and the experimental values, we have obtained that the numerical load is about 86% of the experimental load, which is a good approximation as a preliminary result. Besides, by means of the classical formula for the fracture toughness and by means of the fracture loads obtained before, we have computed the fracture toughness range between the 0.02 and 0.1 megapascal per square root meter, and these values follow the typical power law shape and as a function of the relative density, and they scale with the fracture strength of the base material and with the square root of the unit cell size. Here you can see the plot in logarithmic scale. But we have asked ourselves, are these realistic values of fracture toughness? So on the left here you can see the von Mises stress averaged on one unit cell with an overlap of half cell along the bisector of the notch as a function of the distance from this notch. And here you can see the typical behavior of a stress on a bulk material. But in this case, we have a von Mises stress. And by means of such von Mises stress, we computed a dummy, let's say, fracture toughness as the stress intensity factor of the von Mises stress. Of course, physically, it does not have a specific meaning. However, the order of magnitude approaches the previous ones, and this is a confirmation for the order of magnitude, at least, of the fracture toughness for such material. Another confirmation has been observed by applying the boundary layer analysis, which consists of, before computing the effective elastic modulus of such architecture materials, knowing the beam's elements radius and the beam's length of the unit cell, and using such properties to compute the displacement field of a bulk material under mode 1, and hypothesizing a unitary stress intensity factor, we applied such displacement field around the boundaries of a volume around the notch, and we obtain again the same order of magnitude of the fracture toughness, confirming again that such fracture toughness values are pretty realistic, but future confirmations are needed, of course. Thank you for your kind attention.